Integration is the basic operation in integral calculus, while differentiation has easy rules by which the derivative of a complicated function can be found by differentiating its simpler component functions. Integration does not, so tables of known integrals are often useful. This page lists some of the most common antiderivatives. Historical development of integrals. A compilation of a list of integrals and techniques of integral calculus was published by the German mathematician Meyer Husch in 1810. These tables were republished in the United Kingdom in 1823. More extensive tables were compiled in 1858 by the Dutch mathematician David de Beerens de Haan. A new edition was published in 1862. These tables, which contain mainly integrals of elementary functions, remained in use until the middle of the 20th century. They were then replaced by the much more extensive tables of Grad-10 and Riegeek. In Grad-10 and Riegeek, integrals originating from the book by de Beerens are denoted by bi. Not all closed-form expressions have closed-form antiderivatives. This study forms the subject of differential Gallows theory, which was initially developed by Joseph Liouville in the 1830s and 1840s, leading to Liouville's theorem, which classifies which expressions have closed-form antiderivatives. A simple example of a function without a closed-form antiderivative is e-x2, whose antiderivative is the error function. Since 1968, there is the Risch algorithm for determining indefinite integrals that can be expressed in terms of elementary functions, typically using a computer algebra system. Integrals that cannot be expressed using elementary functions can be manipulated symbolically using general functions such as the Meyer-G function. Lists of integrals. More detail may be found on the following pages for the lists of integrals. List of integrals of rational functions. List of integrals of irrational functions. List of integrals of trigonometric functions. List of integrals of inverse trigonometric functions. List of integrals of hyperbolic functions. List of integrals of inverse hyperbolic functions. List of integrals of exponential functions. List of integrals of logarithmic functions. List of integrals of Gaussian functions. Grad-10, Riegeek, Jeffrey, Zwillinger's Table of Integrals, Series, and Products contains a large collection of results. An even larger, multi-volume table is the Integrals and Series by Prudhanov, Brychkov, and Marichev. More compact collections can be found in e.g. Brychkov, Marichev, Prudhanov's Tables of Indefinite Integrals, or as chapters in Zwillinger's CRC Standard Mathematical Tables and Formulae. Bronstein and Semendyaev's Handbook of Mathematics and Oxford User's Guide to Mathematics, and other mathematical handbooks. Other useful resources include Abramowitz and Stegun and the Bateman Manuscript Project. Both works contain many identities concerning specific integrals, which are organized with the most relevant topic instead of being collected into a separate table. 2 volumes of the Bateman manuscript are specific to integral transforms. There are several websites which have tables of integrals and integrals on demand. Wolfram Alpha can show results, and for some simpler expressions, also the intermediate steps of the integration. Wolfram Research also operates another online service, the Wolfram Mathematica Online Integrator. Integrals of simple functions. C is used for an arbitrary constant of integration that can only be determined if something about the value of the integral at some point is known. Thus each function has an infinite number of antiderivatives. These formulas only state in another form the assertions in the table of derivatives. Integrals with a singularity when there is a singularity in the function being integrated such that the antiderivative becomes undefined or at some point. Then C does not need to be the same on both sides of the singularity. The forms below normally assume the Cauchy principal value around a singularity in the value of C, but this is not in general necessary. For instance, there is a singularity at 0 and the antiderivative becomes infinite there. If the integral above would be used to compute a definite integral between -1 and 1, one would get the wrong answer 0. This, however, is the Cauchy principal value of the integral around the singularity. If the integration is done in the complex plane, the result depends on the path around the origin. In this case, the singularity contributes -I when using a path above the origin and I for a path below the origin. A function on the real line could use a completely different value of c on either side of the origin, as in rational functions, more integrals. List of integrals of rational functions. These rational functions have a non-integrable singularity at 0 for a -1. More generally, exponential functions, more integrals. List of integrals of exponential functions. Logarithms, more integrals. List of integrals of logarithmic functions. Trigonometric functions, more integrals. List of integrals of trigonometric functions. Inverse trigonometric functions, more integrals. List of integrals of inverse trigonometric functions. Hyperbolic functions, more integrals. List of integrals of hyperbolic functions. Inverse hyperbolic functions, more integrals. List of integrals of inverse hyperbolic functions. Products of functions proportional to their second derivatives. Absolute value functions. Let f be a function which has at most one root on each interval on which it is defined, and g an antiderivative of f that is 0 at each root of f, then where Sgn is the sine function, which takes the values -1, 0, 1 when x is respectively negative, 0 or positive. This gives the following formulas. When for some integer n, when for some integer n, when for some integer n, when for some integer n. If the function f does not has any continuous antiderivative which takes the value 0 at the zeros of f, then is an antiderivative of f on every interval on which f is not 0, but may be discontinuous at the points where f equals 0. For having a continuous antiderivative, one has thus to add a well-chosen step function. If we also use the fact that the absolute values of sine and cosine are periodic with period pi, then we get special functions c, trigonometric integrals, a, exponential integral, li, logarithmic integral function, f, error function, definite integrals lacking closed form antiderivatives. There are some functions whose antiderivatives cannot be expressed in closed form. However, the values of the definite integrals of some of these functions over some common intervals can be calculated. A few useful integrals are given below. For a greater than 0, for a greater than 0, for a greater than 0, n is 1, 2, 3, and is the double factorial. When a greater than 0, for a greater than 0, n equals 0, 1, 2. Greater than 0 and greater than 0. C beta function is the modified Bessel function of the first kind. If the function f has bounded variation on the interval a, b, then the method of exhaustion provides a formula for the integral. The change of variable gives an. Under this form the result appears in list of integrals of exponential functions #definite integrals that sophomores dream, attributed to Johann Bernoulli.